Alright, so today we're going to be talking about separating mixtures, basically how we can take our mixtures, heterogeneous or homogeneous, and separate them apart. So, why would we need to separate mixtures? Well, one reason that we might want to separate mixtures is maybe we need something out of it. Think about salt water from the ocean. We have a limited supply of fresh water here on the planet, so sometimes we might want to take the ocean water, which covers a huge chunk of the globe. We want to take some of that salty ocean water. We want to turn it into fresh drinking water, or water that we can use to water our gardens, or to flush our toilets, or take showers, right? Now, that would be why we would want to separate mixtures. What about separating a suspension versus separating a solution or colloid? Remember, our suspension has different size particles than our solution or colloid would. And there is a key difference in how we can separate those. And the other thing we're going to address is how we can use our physical properties to separate things. Now, we didn't talk about magnetism before in the physical properties video, but we did talk about boiling point, we talked about particle size. Magnetism is another physical property that we can use to help separate out certain materials. So we're going to discuss how these different things can work together to help us separate out our mixtures. So separating suspensions. Suspensions can be separated using filtration. Remember, filtration is one of the ways that we distinguish whether or not something could be filtered. Was one of the ways we distinguish between homogeneous and heterogeneous mixtures. So in this case, suspensions can be separated by filtration. Basically what filtration is that we take like paper or a net or some gel even, and we use that as a way, we pour the liquid over that medium. So that would be like, say, the coffee filter in your coffee pot. We put whatever it is we're trying to separate into the filter. What will happen is that the particles are big enough that they'll be trapped by the weave in the paper, or they'll be trapped by the grit in the gel, or they'll be trapped by whatever it is that you're using as a filter. And what will come through in the bottom is just the liquid portion. So you'll wind up with your residue in the filter, which will be your solids, the stuff that was trapped by the filter, and you'll wind up with your filtrate, which is going to be the liquid that came off it. So this is a pretty quick and easy way to separate suspensions. It's why we use Brita pitchers or pure pitchers for tap water, separating out tap water, because we can pour our tap water in there. What the filter does is it pulls out all the stuff like the particles of stuff that might have been coating the pipes that brought the water to your house, or anything that may have been in the sink. It can filter that out and leave you with fresher tasting water. So another way that we use filtration is that we use a process called chromatography. Now, chromatography is it can be a pretty confusing topic for some students. Basically what you have is you have your filter paper, and you're now doing filtration sideways. We typically use this to create quote-unquote fingerprints of things. So you might be creating a quote-unquote fingerprint of an ink. What dyes make up that ink? You might be creating a fingerprint of DNA. You might be trying to figure out what proteins are in something. And we can use this to find it out. Now, is it great for actually getting quantities? Like if you wanted, say, only the red dye from a pen, would you use chromatography to get it? Probably not. It's not going to be able to separate things in bulk. It really just tells us what's in something. So with this, basically what you have is you put dots on your filter paper. And you put your filter paper in some sort of solvent, in this case probably water. And then the solvent will move, it'll get sucked up by the filter. As it gets sucked up by the filter, the dyes will travel down the little tubes inside the paper. The bigger dyes are going to have a harder time traveling, whereas the smaller dyes will go much quicker. Think about it like in the maze of tubes at Chuck E. Cheese's. Say that you have a little teeny tiny second grader, and you have let's say a 7th grader, so somebody who's a little bigger, and then you've got a 12th grader, so somebody who's probably pretty tall, okay? If you put all three of them and tell them to go through the same tube at the same time, what you'll find is that that little 2nd grader, who's teeny tiny still, can easily navigate those tubes, and they get to the end much quicker, whereas your 7th grader maybe takes a little more time because they aren't quite as tiny, they have a little bit more trouble getting through the tubes. And then your 12th grader may be so tall that they don't even fit in the tubes anymore. So sometimes you'll see that inks stay, parts of the pigments may not move at all, and that may be because the ink pigment is too big to travel. Now the other thing to remember with this, especially with inks, is that we have things like permanent markers. Now the entire point of a permanent marker is that it's not easily dissolved in water, right? So if we put water in the bottom of our chromatography setup and try and separate out that permanent marker, of course it's not going to work because it doesn't dissolve in water. So instead what we would need to do is find what it does dissolve in and use that as our solvent to spread out the inks. So that's chromatography. You just need to have a broad understanding of it. So separating solutions and colloids. Remember, solutions and colloids cannot be separated by filtration. But what we can do is we can use boiling points to separate our solutions. This is called distillation. So again, this would be a situation where, let's say that you got all the fish poop and all the sand and the seashells out of your ocean water. You're still going to have salt in that water. Salt water is a solution, okay? So we need to figure out how to get the salt and the water separated. So the way that we do that, we use distillation. What you have is a setup where you're basically heating the water, okay? Now, you've probably never seen salt boil. The reason that you've never seen salt itself, like pure iodized table salt, you've probably never seen it boiling is because its boiling point is so darn high. So there's probably no way you're going to see it boil unless you're working in, like, say, a iron smelting plant, okay? So since our boiling point of water is 100 degrees Celsius, which is much easier for us to achieve in the lab, what we can do is we can take that water, turn it into a gas. The salt's not going to be melting. It's not going to turn into a gas. It's just going to hang out there in our beaker on the top. So as our water boils and it evaporates, turning into gas, it's going to travel up to the top of our apparatus by where you see the thermometer, and it's going to be forced down this tube. Now in that tube we have cold water continually running around it. So as the cold water continually runs around it, it takes that gas and it cools it back down. As the gas cools back down, it's going to get closer to 100 degrees Celsius again. Now remember that 100 degrees Celsius is where we turn from liquid to gas and from gas to liquid. So as it goes lower than that 100 degrees Celsius, it's going to turn back into liquid, and the drops are going to collect on the walls of our tube, our cooling tube. As they collect on the wall, they're going to gather up together and slowly drip down into our flask at the bottom. So what you'll wind up having is your salt is going to stay at the top, and you're going to have your water runoff in the bottom. Now, do you think you can really get every single ounce of water out of the top? No, probably not. So we use this process typically to collect the liquid. Like, we want the thing with the lower boiling point in this situation. If we want to keep the solid, if we wanted the salt, we would have to use a different process. And that process would be evaporation. So again, it's similar to distillation in that you're separating via boiling points. However, in this case, we're using the fact that water evaporates to basically let the water evaporate and collect the salt from it. Okay, so in this case you'd have like a pan of water or maybe some big open area, something like that. Or if you rinse your mouth with salt water, you can always leave your cup out overnight and see what happens to it. But basically what will happen is that you leave that out. Over time your water is going to just heat up or evaporate because it's constantly interchanging with the atmosphere. So your water molecules are going to be turning into gas. They're going to be disappearing. It might take a while, but they'll do it. And once they disappear, the only thing that's going to be left in that tray is your salt. And so you'll be able to collect it easily. So this is an ancient tradition. This is how we get salt from seawater. It's how we get things like Dead Sea salts. And we use it all over the world because it's such a simple, low-tech method. So basically, those are a few different ways that you can separate your mixtures. If you have any questions, please let me know, and please keep your eyes out for more videos.